Very nice. Nice. It's starting to record. Nice, she's also here. Very good. Today's lecture is going to be very easy. Just wanted to ask you guys a very small question. Are you already familiar with GANs?
I think we had lectures about it, but only one lecture. And for me personally, I don't have practical experience, just what we have learned, and not so strong background. I
see.
can yes, but we already know what's GANs and
so what they are and what they do, right?
Yes.
Very nice. Anybody else? For example, Ekichi, how about you?
Hello, good evening. I did not get the question.
Are you already familiar with GANs?
Just the theoretical understanding. I don't really have any practical experience with it.
Nice, I see. So you only know theory, but not a lot of practice. So in today's lecture, we're going to go through the theory again, and hopefully we will go through the practice on not next week, maybe next week, right? I think it's next week, right? Yeah, if I'm not mistaken. There are only 2 students. Okay, we can do the lecture with only 2 students. And how about your projects? Are you guys advancing? Are there some problems?
For us, we are making some progress, although there are some challenges, but we'll overcome them.
You're making some progress, right?
Yes, we are. Thank you, sir.
That's nice. Can you tell me what's the progress that you guys are making?
Okay, so far we have tested, we have a model that is working that can detect emotions using facial expressions. And we are trying to build we are trying to try out different methodologies, different ways of implementing it. So far, the challenge we are currently trying to overcome, there's an implementation we are trying to do in PyTorch, but there are some challenges. We are still experiencing some errors while running the code. Hopefully, before this week runs out, we would have figured that out, and we can try other methods too. And yes.
Okay, thank you. Anybody else, for example, Batul or Sergey? How about your advancements in the project? And Batul, maybe you could...
For us, we're still going slowly. We haven't actually did some big progress. I think that Muhammad sent you a video today, and just trying to figure out, since we're working with hardware, we're just trying to master to exactly benefit from all what we can get from using this hardware, trying to just enhance the readings for now.
Gotcha. Okay. How about Sergey?
Yeah, we start doing our project. We start from just implementing segmentation model on on a simple class like car, and seems like everything is working, but we still have a problem with implementing the same model to another more difficult class like lanes.
Okay, got you. So if I'm not mistaken, the project that you're working on, Sergey, is about line detection and then applying Huff transform, right?
Yeah, right.
Nice. That's okay. So just, sorry. Okay, why is this happening? Let me just check. Sounds a bit better. Okay, so in today's lecture, we're gonna speak about generative adversarial models, networks. First, we will speak about their architecture. So we will speak, since the majority of you already have some experience with GANs, you already know that they are made of two components. The first one is the generator, and the second one is the discriminator. We will speak about each one of these components in a bit more detail, and then we will speak about their loss function, which is a much easier loss function than DAEs, if you have some experience with that. And then we will speak about some variants of GAN, which solve some of the problems about it. In this lecture, we're not gonna cover a very specific question. And for that question, I'm gonna give you two links to read. So this is like, let's call it obligatory reading, or just something to get more points on your final exam. So just for a small discussion, I have tried a lot to work with the midterms like in quizzes or quiz format, or midterms in written format, but usually they're not very effective in evaluating students. So this is why I wanted to maybe in this time try to do oral evaluation. So basically, hopefully next week, or not next week, next week, we're gonna have a quick midterm, which is going to contain like 10 minutes per student. Every student will have like a specific time where they just log into Zoom. I will ask them some small questions, they respond. I see the way they think about these questions, and that will be your midterm. And if it's a successful one also, so if the grades are good and the students like it, we will do the same thing for the final exam. Okay?
Okay.
Very well.
Okay, so it will be on the next week, right?
Yes, next week, hopefully, yes.
Okay.
Not next week, next lecture.
2 weeks from now. 2 weeks.
Yes, 2 weeks from now.
Okay.
And it will only be about, what are they called? Like image classification, and the second one of, what was the second lecture that we made? Image interpretation, right? So interpretability. So concepts such as image instance segmentation, object classification, and GANs will be covered in the final exam. I will tell you all of this, hopefully, right after the lecture. I will send you a bit more of a detailed explanation in the Telegram channel. Now let's come back to our model on GANs. So before we start with GANs, the most important part about GANs is not really the generator part, but the discriminator part, right? So the discriminator model is something that we have all seen before. It's just another classifier following the same methodology of supervised learning. So for example, we take an image of a man, we predict it's a man. We take an image of a woman, we predict it is a woman. So this is what the discriminator is trying to do. Discriminator is trying to classify images into their different categories. Now, in this case, the images come directly with their proper labels. But in the case of GANs, what we will do is we will make these labels up, right? So the labels of GANs will be a bit different than man and woman. They will not be labels that come from the data. These will be labels that we add on top of the data, making it still a unsupervised learning setting. Whereas the generative model part, or the generative architecture, is the following. So usually we give it some latent space or latent code. This latent space can be either completely random noise or can be a value, a specific value. So we've already seen variational autoencoders, for example. Do you remember those?
Yes.
Nice. So remember the content of, or the output of the encoder is called the latent space or the latent code. We can, in fact, send the content of, or the output of the encoder to a generator, and that will be similar to what we are doing in autoencoders. And other people, what they do is they combine randomness with a specific set of classes. So for example, the first 10 values, they will be completely random. And the last 10 values, they will be some sort of an encoding of classes, right? So the last 10 pixels or 10 values will encode information such as the gender of the image, the age of the person, blonde or black hair, something like that, right? So we can have any sort of latent encoding, send it through the generative model, and we hope that the generative model would give us an image that corresponds to this latent code. So just before we go into more details about GANs, do you guys remember what VAEs were doing, right? So VAEs are also a model, a set of models that can perform generative abilities, but they're not the best. So the best models are certainly GANs. And with the main difference between the two is the following, right? So here, this is the generative models, and they are split into two types of models. The first types of models is explicit PDF probability density function formulation or modeling, and this one is implicit formulation of the PDF. What do we mean with explicit? Explicit means that we are explicitly modeling the PDF, like the probability density function, as we are doing in the variational autoencoders. So instead of representing the probability density or probability distribution of images, which is a concept that is much harder for us to work with, what we do is we model a distribution that we define, and then we build a mapper from this normal distribution into the distribution of the images, right? So this is what we are doing with VAEs. We model a certain probability density function, and then from this probability density function, we just make a certain mapping. The mapping is, of course, the decoder that maps a random value from this PDF to a random image, hopefully from the PDF of the training data. This really doesn't give good results because we are still not really modeling the image distribution. So that's, we're just doing some sort of mapping. And this mapping is certainly not going to be perfect. This is why GANs, this is why variational autoencoders do not have very good generative abilities. The other, on the other hand, which is the implicit PDF formulation, in implicit PDF formulation, you do not care about probability formulations. So we do not have any probability density function. We do not have anything like that. The model itself will learn the PDF of the data, but implicitly, right? So he's not going to learn it in some sort of mathematical modeling setting. He's going to learn it in the weights of the neural network. And this is why GANs are a bit harder to train than variational autoencoders, but they tend to give much better results than variational autoencoders. So in here, for example, the only goal of this slide is to basically explain to you guys that the PDF or the probability density function of images can be very difficult to model. So it's something that we certainly cannot easily do. And the goal of, what is it called, of GANs is basically to model this probability density function without having to officially model it, right? So let's take, for example, a certain scenario. This is a hypothetical probability density function of the data. And usually what you will find is lots of different modes in here. For example, this mode corresponds to images of white men with glasses, for example. Let's say this other, for example, this x2 point corresponds to the area where we have women with, let's say women with black hair. Here, this is women with blonde hair, and so on and so forth. So you can see this x is just one-dimensional. Now take this x from a one-dimensional formulation into like 1000 by 1000 formulation. So it's going to have lots and lots of values around here, right? Making it a very difficult PDF to formulate. Whereas here, so these are the special points, or like these are the areas where we don't have lots of representation. So let's imagine this area is here too. So these are the areas where images can be a bit strange, right? So for example, here, these tails represent images that don't really make a lot of sense to us. And this is what all the different generator models are trying to do. They're trying to basically build some sort of a distribution or a mapper from this distribution. If you sample in the region of white women with blonde hair, you should get an output of white women with blonde hair. But if you sample from an area where images or where training images were not really present, your output is not going to be very good. So in here, what we are trying to see is we are trying to approximate basically, or we're trying to estimate the probability density function of the data through the probability density function of the model. As we have said, for models such as variational autoencoders, of course, in our course, we did not go through the mathematics, but if you go into more depth about variational autoencoders, you will see that they have a mathematical formulations of P of X. They have a mathematical formulation of P of data of X and P of model of X. Usually P of model of X is represented as Q of X. And they try to basically bring these two distributions closer together using things such as KL divergence and so on and so forth. Whereas in our case in here, for the generator or the GANs, we do not do this explicit modeling of the PDF, right? So here, the main goal is to basically explain to you guys the differences between GANs and VAEs. VAEs, they heavily rely on the explicit formulation of a probability density function, whereas GANs, they try to learn this probability density function without having to model it in a certain mathematical formulation, right? So they're trying to learn it through the weights of the neural network. They're trying to learn it through back propagation. So here we're going to speak about GANs. So GANs is made up of three different words: generative, adversarial, networks. The most impressive or the most shocking thing about GANs is their generative abilities. The generative abilities of GANs is, okay, there's a question. What method are we using to compare two distributions? KL divergence, yes. Ah, Randall, you're here. Are you in Innopolis, by the way?
Yeah, no, there was some problem actually with my flight. It was cancelled and stuff, and my e-invite, expired on the next day, so I have to reapply again.
Yeah, that's okay. That's okay. These things happen all the time because of COVID. Don't worry.
Yeah.
Nice. So yeah, you're correct. We're gonna use things. Sorry, we can use things such as KL divergence and other distance measures for, or let's not call them distance because distance is symmetrical, whereas KL divergence is not. But are there difference measures between distributions? There exists many of them, and KL divergence is the one that is used for VAEs. Yes. So here, as we said, the three words that compose GANs are generative, adversarial networks. The first part is the most impressive one because they generate images with super good qualities, HD quality of cats, of people, of faces, of cars, of dogs, of anything you actually want them to generate. So their generative abilities are very impressive. But from my point of view, the most important concept that was added in GANs is the adversarial part, right? So the adversarial part is the idea that was revolutionary in GANs. So this idea was completely different, to put two neural networks fighting against each other. So in this case, the two neural networks are fighting against each other to do the generative task. Other tasks can be, for example, domain adaptation, can be domain generalization, can be, I don't know, improving some sort of training. There are different applications of this adversarial learning, outlier detection, and many, many, many more, right? So this idea of adversarial training, or of course, for example, take Deep Zero, right? AlphaZero, no, yeah, take AlphaZero. It's trained on adversarial training. So applications are endless of this idea of adversarial training, and it is one of the few completely revolutionary ideas that were introduced in the field of machine learning since the existence of neural networks, right? And of course, the last part is networks, and just basically we're using deep neural networks to perform this task. Pretty easy. So let's start about the generative models in general. What we have is a set of training examples from an unknown distribution, the distribution of the data. This unknown distribution in case of images cannot be modeled directly with, for example, I don't know, the mean and variance. So all of these concepts cannot really explicitly formulate image distributions. One way to do it would be to convert every image into a vector like this. But as we all know, and of course, treat every single one of these values as just a PDF, right? So each one of them is a normal distribution, but this will not take into account the relationships or the spatial relationships between the different pixels. And of course, we have images of different sizes, right? So this makes things even harder to flatten like this. Somebody would resize it, but still you're removing some of the parts of the data. So here we are, as we said, we have an unknown distribution called probability distribution of the data. And we want to train a model, the generative model, that can basically draw new samples, right? So we want to draw new samples from this distribution of the model, such that model distribution should be as similar to data distribution as possible. So we're trying to estimate basically P data using this P of model. So why do we use these generative models? We can use them to analyze the ability to represent and manipulate high-dimensional images, high-dimensional distributions such as images. They can be used also for text. They can be used also for videos. They can be used as a tool for reinforcement learning. They can be used as a tool, for example, for games, right? So for games, as you are just exploring the world of the game, you are generating new scenes for the player. So this is something that we can do, of course, with GANs, but they're still not at the level that they need to be at to basically do generative training for generative features for complete games, but still it's a possibility, right? They can be used in semi-supervised learning where labeled data is very scarce, and they can be used to sample realistic examples from some high dimensional distribution that can have many, many applications that can, so for example, I don't know, just generating for fun, generating new images of you. For example, if you go to Facebook, like there was a trend on Facebook, like every single day you find a new filter that tells you what you will look like in 10 years, what you will look like in 20 years, or yeah, things like that. What would you look like if you were a man? What would you look like if you were a woman? Something like that. So all of these things can be done with GANs. Other things such as image super resolution. So basically they take a very, let's say, low scale image like this one. And this is even improved. So they take something even worse than this and they generate something like this, right? So this is what image super resolution does. And as you can tell, this quality of the image is 10 times better than this one. And it is very close to what the original artwork is, right? So this is the goal of image super resolution. And if you check this one, this was made in 2016, right? So we are in 2021, going to 22. The results now of super resolution are unhumane, right? So they're so much better than this that you wouldn't be able to, you know, distinguish between the generated image and the original artwork. Sorry. So how was GAN invented? So GAN was invented by Ian Goodfellow. Currently, Ian Goodfellow, I think, is working in Facebook with either in Facebook or in Google, but he's like now like a very, very big name in the field of machine learning. And the idea that he had was just like a very silly idea that he discovered while he was drinking with his friends in a bar. And it was just a joke. Why not put two neural networks to fight against each other? And that joke just came up with the most brilliant and innovative invention in the field of computer vision or the field of machine learning in general for the last 10 years, right? So here, for example, we see the Facebook's AI researcher director, Yann LeCun, has called adversarial training the most interesting idea in the last 10 years of machine learning. And now the same person, Yann LeCun, has said that self-supervised training is the new hot thing, right? So self-supervised learning is, no questions? Yeah. So self-supervised learning is a new concept that is being explored heavily in both Facebook's and Microsoft's and Google's labs. And especially with the introduction of attention and visual transformers to computer vision. So this allowed for self-supervised learning to see the day, and basically lots of new applications are coming for that one. It's certainly something that requires a lot of computations and lots of data, and this is why they're combining it with attention, which also requires a lot of data. So hopefully with some time, these different models that leverage, sorry, I think I should close the window. Can you guys hear any construction work? No?
No.
That's nice, that's nice. So yeah, so as we were saying, this adversarial idea of putting two neural networks fighting against each other is a very revolutionary idea, and its applications are quite endless. So the architecture in general is the following. We take some real images, send them through the discriminator, and ask the discriminator to basically classify them as true or real. And then we generate some random noise. So using some random noise, we generate some images. Remember, this architecture is the same architecture as a decoder in variational autoencoders, right? So it's just upsampling with convolutions from some random starting noise. Of course, the image will be completely random, and the discriminator would just have to predict it as fake. And this is like overall the components of the training. Now, the training of the generator, so the generator, or the goal of the generator, right? So is to generate new images from some prior distribution. Usually this distribution, for simplicity's sake, is normal distribution of 0, 1 or 0, I, depends on what you want. Some people try to, of course, make this random noise a bit more complicated, add more features, add more labels, do a lot of work on that. Anything you can put in here is puttable, right? So whatever you want to think about, you can put it. So as we were saying, so this generator will just take some random noise from any distribution you want, and it will convert it into this shape, the shape of an image. Now the content is the thing that he will need to learn, right? The discriminator, on the other hand, will try to classify real images as real and fake images as fake. So the outputs should be something 0 and 1 because it's a binary classification. And and of course, the discriminator of an image or of an input should be 0 if the discriminator thinks it is fake. So the generator gives fake, gives 0, whereas a real image should give 1. And here we give it the data, right? Or not data, let's call it the real, right? Real image, right? So real equals 1, generated equals 0. This is the goal of the discriminator. And now the goal of our generator, the GAN in general, is to train all of these neural networks against each other such that they both reach a level where they are at their optimal behavior. Meaning the GAN, the generator, is generating super realistic images, and the discriminator is still able to, detect some good images, some real images, detect them as true, but he will find most of them as false and vice versa. So we're trying to reach a place where both the discriminator and the GAN are in somewhat well-trained. They both have reached an area where they cannot improve any longer. And in game theory, this is called as the Nash equilibrium. So basically, the Nash equilibrium means that the loss of the discriminator had reached a local minimum, the loss of the generator had reached a local minimum, and any change in D or G would just decrease their performance, right? Or would increase their losses. There's no real or efficient way to detect the Nash equilibrium. So for example, usually previously for like object detection or image classification, you know that the model is good if, let's say, the accuracy is high, right? If the accuracy is high, the model is good. The accuracy is low, the model is not good. But in this case, there's no real way of understanding because the accuracy in this case has no real meaning. And the generator part does not have, like, how do you evaluate if an image is good or not, right? So this is something like an open-ended question, and any answer you would come up with would only be a heuristic. It would not be like a complete answer. So this is why what we usually do is we let it train sufficiently enough. So sufficiently enough is something that you personally would judge as somebody who has trained lots of GANs. You would know for this problem, it should take 2 or 3 days to finish the training. Let's say something like that. And after it has trained sufficiently enough, usually a very good index is the discriminator should give very vague answers, right? The discriminator should not be very sure of himself, saying this is real, this is fake. He should be giving, what are they called? Vague answers. So let's say this is 0.6 real, 0.4 fake. He's not very sure about himself, and he shouldn't be able to have very good accuracy. So usually his accuracy should be 0.5. So this is just a small indicator, but it's not, that does not mean in any way that every time you have accuracy equals half, meaning you have reached the Nash equilibrium, in no way. Now the loss function, as you can see here, of GANs looks very, very scary. But in reality, it's a very simple concept, right? So it's very basic. This is, both of these are your discriminator loss. Basically, you're trying to send, what are you trying to do, right? So you're trying to maximize over D, so maximize over the discriminator, both of these terms, because these terms are both of them included in the discriminator loss, and minimize over G. This term, because this is the only term that contains G, right? So this term contains D, this term contains D. So both of these values must be maximized over D, whereas only this term is containing G, so this term will be minimized. Now, studying the loss function in this formulation is very difficult, but splitting the loss formulation into different parts like this will simplify the job for you, right? So let's take it a bit easier, right? So the discriminator's role is to basically distinguish between the real and fake, whereas the generator's role is to confuse the discriminator, making him feel like fake images are real. Can somebody tell me what does it mean fake images are real, right? Or predicted as real? Previously, what we said, real means the predictor predicts 1. Fake means predictor should predict 0. The discriminator's job is to do this. Now, the generator's role is to do what? Is to make the discriminator discriminate F as what?
As real.
As 1.
As 1, right? So you all agree, right? So we're trying to send fake images as close as possible to 1. And this is the goal of the generator. So this is generator, this is discriminator. So we can clearly see that 1 is going in the opposite direction, and this is where this is minimized and this is maximized, leading to the results that we have, the loss function that we have. So here, as we've said, this is the data, probably the distribution of the data. In the beginning, the distribution of the data that we learn is very random, useless. But after a set of iterations, we try and approximate this probability density of the data using the probability density of the model that was learned by the model, sorry. And we do that by adjusting the weights using the backpropagation. So, sorry, let's, this we already did it, right? So here we'll just take a look at what is a binary cross entropy. So this is the formulation of the binary cross entropy loss, or this is the case when it's not binary cross entropy. So this is where it's like has lots of values. But in our case, for example, here, what do we have? Y times log of y hat plus 1 minus y log of 1 minus y hat. So let's take a look at it. Y is the label, and as we said, it can be either 0 or 1. So can somebody replace 0 in this formulation and tell me what do you get? 0 times something disappears, 1 minus 0 becomes like 1, right? So let's say this one disappears, and we are only left with log of 1 minus y hat. Whereas when y equals 1, so it's 1 times log of y hat plus 1 minus 1, so this is 0, 0 multiplied by something, all of this disappears. And this is the loss function when y is equal to 1. So this is what binary cross entropy is. Just a small question, I'm sure the like the master's, second year master's students have already seen what binary cross entropy is. But for Randall, have you already studied binary cross entropy or cross entropy in general, like with Professor Khan, seeing things such as decision trees? No?
No, we haven't done decision trees.
You haven't done decision trees yet?
We've just started like neural networks and CNNs.
No way. Like, I think you must have missed a lecture because decision trees.
I attended every lecture. There was no decision tree lecture yet.
That's impossible. Like, he should finish now. If he has arrived to neural networks, that means he's finishing, right? Well, that's weird. But that's okay. Probably they just changed the course a little bit, right?
By the way, one question, like if the label is 0,
yeah,
the predictor will be some negative number.
Why? Why do you mean that?
Y is 0 here, so y log y predictor is 0.
That just disappears.
Yeah, 1 minus 0 is log 1. Log 1 is basically 0.
No. It's log 1 minus y hat.
Ah, okay. Okay.
Yeah, so it's log 1 minus y hat. This is like a complete thing, right? Thank you for pointing this out. So it's log of 1 minus the prediction. This is the prediction. So the loss function, basically, when we have y is 1, so when y is 1, what does it mean y is 1? Means it's real image, right? So the real image, we're trying to get log of y hat to be smaller. We're trying to minimize log of y hat. Whereas when y is 0 or fake image, we're trying to minimize log of 1 minus y hat. So let's take a look at it. Y hat is a value between 0 and 1, right? So log of a value between 0 and 1, how does it look like? It should look like this, right?
Yeah.
So this is where 1 is, right? It's from 0 and it's always a negative number. So we're trying to minimize this negative number. Whereas log of 1 minus y hat, can somebody tell me how does it look like? First, do log of minus y hat. Think about it, right? So this is log of y hat, log of minus y hat. How would it look like? Simple. Okay, log of minus y hat. If y hat is 0, how much is this? Log of 0. What is log of 0?
One.
Log of 0.
Infinity thing, small minus very, very
Minus
small.
infinity. Now,
Yeah.
let's say y hat is 0.2. It's not defined, right?
Yes.
Okay, let's do it with log of 1
Should be
minus
log
y
time.
hat. Let's do it like this. So log of 1 minus y hat, where y hat is 0, what is it equal to?
0.
0, right? So we are at this point. When we have log of 1 minus 0, we are at 0. So this point belongs to our graph. Now let's go to 0.2. Log of 1 minus 0.2. What is it?
That's, we'll get a negative value, minus 0.0969.
So minus 0. Log of 0.8. Log of 0.8, right? So when we
Yes.
are at 0.2, at this point, we
Yes.
should be at a negative.
Yes,
place.
minus 0.01, 01, minus 0.1.
So just
Approximately.
like try to think how it would look like, right? So it would look like something like this. The other one looks like this. This one looks like this. Хорошо?
Da.
Да. Nice. So this is just to show you guys how these two loss functions look like. One is going like this, one is going like this. Now let's continue. So this is just a small example of what cross entropy is. For those who still don't know what cross entropy is or how to calculate cross entropy, you can go through this example at home. So basically what you can do is, well, let's do it together like quickly. So we can treat one hot encoding as probability distribution for each image. So this is, for example, probability. So a dog would be labeled like this. where the probability of a dog is 1. All the other things have 0 probability distribution. Probability of a fox is 1. The others is completely 0. So we would like to calculate what is the cross entropy loss for this Q1 with regards to P1, right? So P1 is a dog. So in this case, 1, 0, 0, 0, 0, multiply this with this, with this, with this, most of them will be completely gone. So it's the minus sum of P1i, so 1, multiplied with the log of Q1i with this. These will stay, all the rest will disappear. So it will be minus log of 4, which is 0.16. Again, this is just something that you guys can easily do at home, just to learn what is every single one of these. So for example, here, this is 916. This is 0.02, meaning this one is very, very far from being a dog, whereas this one is very close to being a dog. Why? Because this probability is very high, the rest are very low. Whereas in this case, this probability is not very high and the rest are not low, right? So this is very far from being a dog. This is very close to being a dog. Now, binary cross entropy is kind of a simplification of this cross entropy in general. So in this case, we usually just have two labels, which is...
Sorry, one question.
Yeah.
PI and QI are vectors representing what exactly?
PI is this. So this is the one-hot encoding of the label. This is the real label. This is the prediction. Is it getting better now? Right? So this is what the model gives. This is the true value. Хорошо? Okay. So in binary cross entropy, binary cross entropy is like a simplification of these two, where we only have two classes, right? So this negative sum becomes just the following, right? So minus probability of being a cat times log of Q being a cat, minus P of being a dog times log of Q being a dog. Usually if this one is 1, the rest is 0, right? If this one is 1, the rest is 0. Because these are one-hot encoded probabilities of the labels, and usually we have just one label. So using the following relationship, we could just move things around a little bit, and we would have binary cross entropy equals minus P times log of P hat minus 1 minus P times log of 1 minus P hat. And this is done by the following. So basically P of dog equals 1 minus probability of being a cat. Why? Because you don't have much options, right? So the probability of being a cat plus probability of being a dog should be equal to 1, right? Why? Because this is a binary classification setting. And in the end of the activation, we must have something that is treated as a probability function or probability values. And the sum of probabilities over all the different events should be equal to 1. And this is why we have this formulation. Replace this formulation in this loss, and you get the beautiful binary cross entropy formulation. So it's minus P times log of P hat minus 1 minus P times log of 1 minus P hat. To simplify this a bit further on, or to go on and do it, so we will have two, as we said, if you replace the prediction, or if you replace the label with 1, the y in this case with 1, you would get only this part disappears, so you will get the log of d of x. Whereas if you replace it with 0, you will delete this one and keep only this part, right? So you would get 1 minus 0, which is 1, log of 1 minus d of g of z. Z is our latent distribution or our random value from here, right? And now we will have our objective of the discriminator is to basically, let's remove this maximize, is to minimize minus log of d of x minus log of 1 minus d of g of z, right? So this is the goal of GAN, is to minimize minus this value minus this value. So the minus comes from the description, you see, this is from the description of binary cross entropy. So we're trying to minimize the loss. The loss contains minus here and minus here. Minimizing something negative comes back to maximizing the positive version of that. So this is the loss function of the discriminator, right? So it's maximizing this part. This part is the negative of the loss. So this is how it is being trained. Whereas the generator, so the generator is trying to basically maximize this value. And maximizing this value, trying to put it to 1, means minimizing this value. Now, if you just go back to the original function, you will see that he is trying he's trying to maximize the log of 1 minus d, and log maximize minus the log, sorry. So he's trying to maximize minus the log of this value, and maximizing a negative value is the same thing as minimizing its positive version. And ta-da, you get the beautiful combination of the two values. So the author of the paper decided to combine them both in this formulation. This formulation is not going to be used for coding. So in coding, you're going to have this loss function separate and this loss function separate. Things will be very easy. But just if you want to read the article or read the paper and you see this long loss function that looks a bit confusing, it's simple, just a combination of these two loss functions. And these two loss functions are also very simple. It's just binary cross entropy. So this is now, at least you understand the story behind this long formulation of the loss function. I think we could take a small break of 5 minutes and come back after 5 minutes and finish the lecture of GANs. After that, we will take a break of, let's say, another 5 minutes, and we will speak about, what are they called? About your progress in the projects. And then from there, we will speak about the progress in, or let's say, speak about the way of evaluating the course. In that case, I will ask you guys some questions, whether you prefer a quiz format or do you prefer something like, as I said, an oral examination where every student just gets exactly what they deserve. The questions that I will ask are completely simple. There will be exactly the questions that I would ask on the quiz, but you wouldn't have any chance of, for example, miscalculating or misinterpreting the question, because you can directly ask me to just explain the question differently or something like that, and you would always get the grade that you deserve. So this is why I want to go for oral exams instead of quizzes or just written exams. So enough about that. See you guys in 5 minutes, and we will finish the lecture. Hello again, everybody. So now we just have the simple part of the GANs, which is the training. So for the training of GANs, it's pretty simple. It's pretty straightforward. I'm sure everybody would have already guessed it by now. So what we do is usually we train the two different, what are they called? Models, or the two different sub-components of the GAN separately. So usually what we do is we start by training, the discriminator, and then we just go to the generator, go back to the discriminator, then go back to the generator, go back to the discriminator. So for example, 10 epochs on this one, and then 10 epochs, 10, then 10, 10, then 10, in a sequential manner until, as we said, we reach the Nash equilibrium, or we feel like we reached the Nash equilibrium. So as we said, the convergence can be very difficult to identify. So this is the alternative training, and it's a very common way of training GANs, which is you train the discriminator for one or more epochs, train the generator for one or more epochs, repeat these two steps until you had your fun, right? In order to do that, usually when you are training the discriminator, the generator is completely fixed, so the weights of the generator do not change. When you are training the generator, the weights of the discriminator do not change. So this is like the algorithm in simple words. It's saying exactly as we were just saying. There are some small techniques or some small changes to the GANs. I will describe one of them, which is here the change in the loss function. But there are many, many others. So this one says modification in the generator's updates. So this trick is pretty simple. So this is the loss function of the GAN itself. So here, when the sample is likely false, we want to give a feedback to the generator using gradients. Likely false means that the results are mainly here. But you see in this area, the gradient is very small, or the direction of the gradient is very small, meaning the information that is being sent to the generator is not very useful. So however, in this region, as we said, is very close to zero, and the curve is very flat, meaning the gradients would be very close to zero and not very useful for training here. So what we do is we replace it with something that is very close to it, right? So this is a loss function. Again, the same thing. So it's a decreasing loss function, right? So they're both similar. They both represent the same thing. But this one has a special property, which is that the fact that closer to zero, this value is close, or this value is very curvy, right? So you can see that this is a very curvy loss function. And it is very common to see this one replacing this one in the training of GANs, right? Yeah. So here, as we said, just the modification of this one. Adversarial networks have a very great advantage because Markov chains are not needed. You will see Markov chains probably, I think it's a course with Professor Suchi. Yeah, he will give you more details about this one. And again, as we said, only backpropagation is used to obtain the gradients, is used to learn the probability density function of the model. So there's no explicit probability density function of the model. We're just using backpropagation to learn it through the weights. And no inference is required during the learning, and a wide variety of factors on interactions can be easily incorporated into the model by just changing the input to the generator. Main problems in the training of GANs is non-convergence, which is something that we have already seen, and mode collapse. Mode collapse is a very simple concept. Like let's say we have a data set of images of what's his name? Like just faces of celebrities. So if the generator, for example, was able to generate just one perfect image of Mr. Bean. This image is very perfect, right? And he always generates this image of Mr. Bean perfectly. Give it to the discriminator. The discriminator will see, oh, it's a perfect image of Mr. Bean. This is a real image. Now the generator, again, is doing a good job. Discriminator is being fooled, but is the generator useful for us? Since it's regenerating only the same image again and again, the generator is not very useful. And this is something that happens a lot of the times, right? So once, for example, the discriminator starts ignoring all Mr. Bean images, you will find that the generator starts to predict only images of the rock, right? And then once the discriminator picks up, he will remove the rock and he will go to something, I don't know, like Selena Gomez, right? So this is what mode collapse is. Mode collapse is that the generator keeps on repeating or generating the exact same image again and again. And this is a very big problem in here. The solution to this problem is pretty simple. We train multiple generators. So this is generator 1, generator 2, up to generator 500. And the discriminator now is not just predicting if it's real or fake. He's predicting if it's real. If it is fake, where did it come from? Where did it come from? By this, you are enriching the, what is it called? You are enriching the gradient that is coming back from this loss function all the way to these, forcing each one of these generators to learn different images such that the discriminator does not pick up to them pretty quickly. This is one way of doing things. There is another solution to this problem, which is something that I'm going to give you in the optional or the obligatory reading of this lecture. Just a few more solutions in here, but I will not go into more details about them because these solutions, you will find them in the optional the obligatory reading. And it simply is about scaling the values between -1 and 1, using tanh for the output layer of the generator, experiment sampling Z with Gaussian distributions, batch normalization often is used for stabilizing the training, use pixel shuffle and transpose convolution for upsampling, avoid using max pooling for downscaling, use stride instead of max pooling, use Adam optimizer instead of stochastic gradient descent, add some noise to the real and generated images before feeding them to the discriminator. Final remarks, they are currently generating the sharpest images, the best state of the art, easy to train. So they're easy trains and there's no statistical inference required for them to be trained, and only backpropagation is used to obtain the gradients. And GANs are certainly difficult to optimize due to unstable training dynamics and to inability to find the Nash equilibrium. Just some active areas of research. So better loss functions, as we have seen, more stable training. So there's this loss function, there's this new gain, WGAN, there is LSGAN, and many other GANs, which are just changing in the loss functions. There are conditional GANs and GANs for all types of applications. Again, so these are just a few more reasons why we can use GANs, such as the design of the generator has very few restrictions and can be used for CNNs or LSTMs for text, images, videos, anything you want. The GAN doesn't require any variational lower bounds, such as variational autoencoders. So for those who took a course properly with Professor Khan or advanced computer vision, advanced machine learning, should know what is the lower bound for the variational autoencoders. But it's if you don't know it, just completely ignore it. GANs are asymptomatically consistent. GANs are subjectively better at generating samples. Sampling is very straightforward, so you just send some noise. Training doesn't involve maximum likelihood estimation. such as, I forgot which model uses the maximum likelihood estimation, but it's a pretty horrible model and doesn't give good results. Robust to overfitting, since generator never sees the training data. This is very important. So the training data is only being sent to the discriminator, and the generator is never interacting directly with the training data. Empirically, GANs are good at capturing the model's distributions without having to explicitly model the distributions. Applications are endless: image-to-image translations, text-to-image synthesis, face aging, and many more. So this is what image-to-image translation. You take an input like this, just a segmentation, and it generates what it would look like in the reality. You take, for example, labels, and it would generate what the building would look like. Black and white to colored images, edges to a real photo, day to night, input to output, right? Text to image synthesis. So for example, you give it some description and it generates it. This small bird has a pink breast and a crown and black primaries and secondaries. So here, for example, you take a look at it. These are generated images only from this text. And you can definitely see that the colors are kind of respected in here. The flower has petals that are bright pinkish purple with white stigma. So you can definitely see that it was generating something realistically. It's not very realistic, but it's also, again, in 2016. Definitely by now we have something much, much better result than this, but it takes more time to train, right? Face aging, for example. This is something that you find in Facebook, right? Image in painting. So for example, you give it an image with empty values here or cropped out areas, and he will regenerate them. Creating art. Some optional reading is to read the original paper if you would like some more information. And thank you, guys. Do you guys have any questions about GANs in general?
Yes, I have a question. Sorry for I didn't get the point of fix the problem of regenerate the same image many times.
Okay, let's think about the problem. Let's put the problem in real life here. So this is what's happening, right?
Yeah, this.
So this is what the data should look like. This is the real distribution of the data. This is what we expect the model to give, right? He's learning, and in the end, he should have a distribution similar to that of the data. But the model is doing something else, right? So the model is learning one mode at a time. And at every step, he just keeps on changing it, right? He just keeps on changing what mode to predict. And like that, he just keeps on repeating the same sample, and he is within our expectations. Now let's try to generate this problem here. Let's call this generator Muhammad. Let's write it in English, right? So let's write it. This is Muhammad. This is generator Muhammad. This is generator Sergey. And this is generator Batul. Let's say generator Batul has fallen in the problem of mode collapse. Right? So let's say Batul keeps on repeating the same instance again and again. The discriminator would now be able to pick up on its image. So the first time he does it, the first time Batul sends this same image again and again, the discriminator would be fooled. But after a few iterations, the discriminator would be like, Batul, stop doing what you are doing, right? So the discriminator would be able to give much better, what is it called? How do you say this? Much better gradients to the training of Batul, and hence Batul should have better results. Technically, this shouldn't, this doesn't work perfectly, so it has some limitations, as you can see here. GANs often seem to collapse to far fewer modes than the model can represent. So usually in here, if you have 20 generators, you should not be able to collapse to at least 20 different images, right? So you should be able to collapse to different types of images. This is not perfect, so your generators are still not perfect. This is the worst case scenario. You get 20 images, 20 different images. This is the worst case scenario. Of course, it's still not optimal. There are better improvements, but this is one way of solving the modal collapse. Instead of repeating the same image again and again, now at worst case scenario, you are repeating 20 different images. Did you get the difference?
Yeah, kind of, but so like for each generator, it will generate one class only, and we will feed to it one class only. So if we have like 30 class, we will need 30 generator or something.
No, not class, right? So this is generating faces of human beings. This is also generating the same faces of human beings. This is also faces of human beings. As you can see, the weights are the same.
Okay.
So we have like the training of this one is the same as the training of this one is the same of the training of this one. But in this case, if in here it is repeating the same image again and again, we will be able to say, let's say this is Batul. Batul, stop doing what you are doing and fix your problems.
Ah, okay, I got you. Yeah,
Got
I
you?
Yeah.
Хорошо. Nice.
Thank you.
You're welcome. So this is a very cool trick. It's a very expensive trick. There are much easier tricks, but it does work and it gives a better improvement. In worst case scenario, it gives better improvements. In general cases, it will solve the problem of modal collapse completely. But worst case scenario, it will improve the situation of modal collapse. Anyone else has any questions?
Yeah, will we see some example of GANs on practice?
Yes, next week, hopefully we will have like a lab, or maybe we can do it now if you want. Let's see.
I have a question.
Yeah.
In the whole GANs model, first we're training the discriminator on the training images, right?
Uh-huh.
That's what's happening, the first step, right?
Can you repeat? On the old GAN model, we what?
No, in a GANs model like architecture, we are training the discriminator on the training images first, correct?
Yes.
And then we're feeding the generator to the trained neural network, the discriminator.
Yes. So we start with the discriminator, then we go to the generator, then we go to the discriminator, then the generator.
But training of training of discriminator is only once. And then we give random noise, and then the generator does something and gives it to the discriminator.
But we continue iterating, right?
Yes, yes.
So first we train the discriminator. Discriminator is trained. Nice. You freeze the discriminator, then you go to the generator. Generator is trained. You freeze the generator, unfreeze the discriminator, and train it. And then you repeat.
But why are we training the discriminator again?
Because the generator has changed. The generator became smarter. So the discriminator must become smarter again.
Okay.
So the discriminator, for example, first situation, let's say this is the real Mona Lisa. And I'm trying to build the generator that generates the Mona Lisa. So the generator from the start would give you something like completely random like this. Discriminator would look at this one, easy to distinguish these, right?
Mm-hmm.
So it will train for the classification very fast. You get good results quickly. Now let's say we froze it and then we trained the generator. The generator now improves. And he would give something like this, let's say. Again, the discriminator will look at this. This is something new to him, right? He has no idea if it's real or fake. So what we do, we train it again, we train the discriminator again on this one and this one, and he learns the differences. Now, if we train the generator again, the discriminator will have more informed gradients. What does that mean? That means that the generator will have to improve his generation techniques. So the generator will have to, improve his results, and he will give something like this. This is something very common between CUPS and thieves, for example. So CUPS, they always develop new techniques to develop, to distinguish real from fake images, whereas fake artists or these thieves, right? They keep on developing new techniques that beat the techniques of the CUPS. The CUPS will learn about these techniques and they will try to beat these new techniques. Thieves learn about the new techniques of the CUPS, try to bring new techniques, and they keep on iterating again and again. Did you get it?
I see your point. Like, I think my confusion was if I'm already being trained on millions of Mona Lisa training images, like I will have a very good trained neural network model, meaning
but why would you need a very good, why would you need it, right? So if, for example, this is the Mona Lisa, very simple. And this is the image of the generator. Any kind of simple classifier would separate these two. Now, if I improve my generation ability and I put it here, right? So this is the new generated image. It's different, but the classifier that I learned is not smart enough to classify this correctly. I need to learn a more complicated classifier. So you see?
Yeah.
This is the point that you are interested in. This is the real point. This is the first fake point. Classifier is made here. Now the generator is trying to put his points on the other side. So the generator for the second step would bring his image here, or would bring his images to this place. Old classifier cannot work here, so the new classifier will have to do this. And then the generator would see this problem and try to put his next points here. So the discriminator now is fooled, so we have to train the discriminator again. Sorry, and the discriminator would try to do something like this. You see, the more you improve the generator, the more you have to improve the discriminator.
I see.
Because the discrimination that you have learned at the start was very simple. Anyone can fool it. Okay?
Okay. And when
so this is the lab of GANs. The lab is pretty simple and pretty basic, but I don't think we should go through it today. If you guys want me to send it to you like right now, I will send it to you right now, but I prefer that we go through it like next week. This way we will have enough time to understand it better. Okay, here we go. Do you guys have any questions about GANs?
I have last question.
Yes, go ahead.
So like we are training the discriminator and the generator at the same time.
Yes.
But how, like, maybe like we are improving both, even the discriminator like is trying to learn and improve, but when we know when to stop, because like maybe at some point it will be it will reach Nash equilibrium. Yes. Without like reach the end even.
So the loss function of the GANs usually look like this, right?
Yeah.
But throughout the end, they get smaller and smaller like this, like the changes become smaller like this. When you reach the Nash equilibrium, they should look like this. They're still going up and down, but they're not changing that much. Here you stop.
Yeah, I got you. Thank you.
You're welcome. Any other questions? If no questions, then let's take a small break of 10 minutes. And just please, one person per each group, prepare a small, just description of what you have done, what you would do, and just to make sure that you guys are still on the right track, okay? After we finish that, I will give you your second homework, and yeah, and we will discuss how to do the midterm. See you in 10 minutes, guys. Hello, everybody. So I hope you guys are ready. Can you guys tell me what? So let's see who should start. So from my side, I see Albatul Yassin. She has already told me like the progress of her group. After that, I see Ikichi and Sergey. So then there's Randall, Mohammed, Abdulaziz, and Valeria. So Randall, let's leave you till the last. How about Mohammed and Abdulaziz? So you guys are with Albatul, right?
Yes.
So far, she told me you guys are working on learning how to extract images from the hardware that you are working with and things like that, right?
Yes. We are using the RealSense camera, and we
Yeah.
have like the information from the RGB image and the information from depths. And what we are trying to do is after like feed our image or inputs to a model like YOLO or something to detect the object, or even a model that we trained ourselves, and it gave us a boundary box. We like make some algorithm for this boundary box, some classical computer vision to make take the boundaries, and then like with the help of the depth information and make a fusion between both information, we are trying to enhance like the segmentation of the object itself. And I believe like this can help us like to make like to label our new dataset in any dataset we want faster than like going to a website and labeling it manually. That's our idea.
Okay, got you. So for now, I just wanted to give you guys a small update on something that you guys can either do or you could give it to somebody else to do, right? Or maybe like you could do after this one.
I couldn't understand.
I'm just gonna show you something, right? Just gonna show you something pretty quick.
Okay.
So this is called SWINT or SWIN transformers. And it's a very cool new architecture that is based on, or it's like an improvement over visual transformers. And visual transformers are just an improvement over, or just an application of the transformers, which were created for natural language processing and gave us the attention, applied to computer vision. So what do they give you is that just they give you an encoder part that is very cool. And using this encoder part, you guys could do something like the prediction of the mask. So only thing you have to do is take a pre-trained SWIN transformer on a data set, like a large data set, and then you just train a simple, I don't know, decoder, just like in an autoencoder setting, where you take, let's say, the latent space of the SWIN transformer, and then you convert it into the depth map, right? Of that, the depth map that you get from, what is the name of the camera again?
RealSense camera.
Yeah, you just convert it into the depth map of the RealSense camera. This will be a super cool application because this architecture is pretty recent and it's getting really all the attention in computer vision field lately. So it would be very interesting to see this application, something very creative, extremely state-of-the-art, and definitely something that you guys would, that's publishable in a very big conference. If you guys cannot do it like right away, you could maybe do it after the course, or you could do it, or you could just give it to some other master students or first-year master students or some bachelor students, whatever you want. They could work on it. This completely depends on your availability and what you guys want to do with your PhD. Or not PhD.
Can I ask? This is trained on a large dataset, like something like Coco dataset, and then it gave us like a segmentation for the object itself.
No and yes, there is something that does object segmentation or instance segmentation already, like this one.
Okay.
But I want you to take the backbone, only the backbone, and train something else on it. Train a decoder for the, what is that called? A decoder for, help me out. What is that thing called? The depth, right?
Depth, okay.
Yeah, just a decoder for the depth.
So like this architecture is decoder, encoder, and decoder?
No, this is an architecture that gives you a gives you an encoder.
Okay.
You must add the decoder on top of it.
Okay, and what is the depth is doing here?
You're just going to create a model that takes an image, RGB, and predicts the depth. How does it predict the depth? Using transformers. Did you get it?
Okay, so here they are doing something like this. So they give like a depth or
No, they give you nothing. They just give you a latent space, right?
Okay.
They just extract some features from the image. You, from these features, will predict this depth map.
Okay.
Mm-hmm.
I don't know if this is applicable, but we'll read more about this and we'll try something.
Okay,
like this.
so this is definitely something that you should do after you finish what you are doing right now.
Okay.
Nice?
Nice. But what we are doing right now is like I want to take some feedback from you, from your side.
Yeah, go ahead. Show me something. Maybe show me what you're working on. Show me what you want to show me, whatever you want. And I'm here.
Okay. Okay. Just a moment.
If you want, you can prepare what you want to show me, and somebody else passes before you. Hello. Maybe Sergey or Valeria Zanina can present what their progress is.
I can present. Can I share my screen?
Ah, yeah, of course. Let me share it.
Show something.
Now you can, yep.
So yeah, as you know, our task is just semantic segmentation of the lines, and
Yes.
we just find some problem in the task definition itself. The main problem that we find that the best solution for that model, it won't be a semantic segmentation model. It will be just some regression model, because it really does not matter what is the width of the lane. We need only the information about like where is the line itself.
Mm-hmm.
So the better model will be like do something like this, like just predict some points on the lane and just creating some formula just to present a lane on the picture. Semantic segmentation is not a better model choice for the task. So we're thinking maybe we can change the goal class of the model on something different.
Okay, certainly, yeah.
So yeah, and we just have some progress with the semantic model on the simple class of the cars. Yeah, like that. Oh, you can see, yeah?
No.
Yeah. That's the result.
So this is for cars.
Yeah. Can you give some suggestion or ideas about the goal task, maybe?
So from what I understood, the goal was to predict the lanes, right?
Yeah.
But why are you working on cars exactly?
Cars are just for example, we just test how our unit model works.
Okay. So this is just to test the model. Okay.
Yeah, right.
Nice. So now just apply this model on the data that you have or the data that you annotated. Once you get the results, then we will explore this further. So what I was hoping to see was once you get the results, you apply some sort of edge detection technique. And on top of the edge detection technique, you apply Huff transforms. Okay, so it should be something like this. Semantic segmentation. After you get it, you apply edge detection on the prediction mask. After you get that one, you apply Huff transforms on the edge detector results.
Yeah, okay.
Хорошо.
But there is one problem, just semantic segmentation. The first part of that work won't be suitable, I believe, because a regression model just give us better results for it.
That's something to see, right? So if you say it's not gonna be good, you need to prove that, right? So you need to train it and then show it's not good. Theoretically, it should be very good.
Okay, we will try it.
Nice.
Okay, thank you.
Thank you so much. Great work. Should we go to Ekşi?
Okay.
Maybe you'd like to add more?
I'm ready. I can show.
Mohammed, you're ready. Go ahead.
Yeah, it's just like got freeze because I was opening the terminal and the stuff.
That's okay. That's okay.
Okay. Okay, I am now holding the camera. Hope you can see my screen. So this is like object. It's a cup, and as you can see, it can give us like this boundary for detecting this cup, and it can give us like you can see here depth and height. We are still working on this. We can estimate the height of the cup, and the depth. Sure, the depth is like wrongly estimated, but like because we have a lot of outliers, so we are trying to remove these outliers because it depends on the accuracy of the real sense, and it's like low accuracy. It has low accuracy, so we're trying like to like come over these problems. And what we are trying to do else is that we have this bounding box, and we are trying to do some classical computer vision to get the boundary of the cup. And with this depth map information, as you can see, we are trying to fuse both information together, so we get better segmentation for the cup from the background that we are trying to do.
I like it. Yeah, sounds like a very nice idea. So you're basically saying depth enhanced image segmentation, something like that.
That we are trying to say.
Nice.
Yeah, because like the RGB image itself or the models, it will be like if you use like the depth information with this, it will like give more accurate results. Supposed to give you more accurate results.
Yeah, go ahead for it. That sounds interesting.
Yeah,
I would like to see some results for this one. Yeah.
Okay, thank you.
Thank you. So I think Iggy has already presented. If you want to say more, please feel free to present something or show me something.
Okay, I can show you what we already have at the moment,
Go ahead.
although my partner is not around now. He's
That's okay.
the data science student, and they have a hackathon today.
Yeah, he told me, yeah.
Okay, just a moment.
Mhm.
I'm trying to share. Okay, can you see my screen?
Perfectly, yes.
Okay, the current model that is working is based on this library called DeepFace.
Mhm.
However, I've detected some drawbacks. It's not very accurate compared
Mhm.
to when you build your convolutional neural networks, you use other deep learning approach to solve this problem.
Mhm.
So I'll just run it on some images where it accurately detects the emotions, and then I'll also run it on some other images. I noticed that in some other images, it did not detect anything. In fact, there was an error. It did not detect any face at all.
Okay.
Should I run?
No, just show me the execution already. It's I think it's already saved. So
Okay. This is for the first image, image one.
Mhm.
It accurately detects the emotion as happy. It detected the dominant emotion as happy.
Mhm.
Actually, this library can detect other things, the age, the race, and other things, but I just focused on emotions. That's why we have these actions here as emotion. So after running it will annotate. What I have here is just a function to annotate the image, and it put the result of what we got, and then to detect the face. And then I also did the one for real-time images. However, I also noticed that when the illumination, when the lightning here is not good enough, maybe this place is dark, it doesn't really perform well. It brings up an error.
Mhm.
I have to maybe use a torch to enhance the lightning. That's the
Just please
drawback.
use something about deep learning, right? So use
Okay.
something deep learning based.
Okay, I'll do that. The other model I told you about, we are building on PyTorch. We're still getting errors there. So I'm sure we'll solve that problem.
Mhm.
Yes. So this is what we have done so far regarding implementation.
That's good. That's good so far. Okay, that certainly does require a little bit more work from your side. So please try to get something like deep learning based and try to be creative about it. But for now, you are like working on a very interesting topic. So please keep that in mind and try your best to get something that works like impressively, right? That does give good results. But you're
Okay.
doing very good work so far. Yeah.
Okay.
Congratulations.
Thank you.
Excellent.
And then I noticed something. I was going to mention it. In the deep learning approach we
Mhm.
got based on that paper, the title of the paper is Deep Emotion, Facial Expression Recognition Using Attentional Convolutional Network.
Mhm.
The best results they got based on their proposed model, they got, accuracy now, the best accuracy they got using the data set, FER 2013, using that data set, they got 70%, 70.02%.
Mhm.
So we're hoping that when we work on this, we can maybe get a higher accuracy.
Just get something close.
Okay. Okay, thank you.
Thank you so much. Just close enough would be amazing already. Okay, nice. So maybe Randall, do you have something to present, or maybe I know you're not the graded students, but if you have something that you are working on or something you want to discuss, please feel free.
I've not coded anything yet. I've mostly just been reading stuff online. So my project is supposed to be instance-based interpretability model. So like you suggested last time, taking up an object detection model like faster RCNN and using GradClam to get a sense of what's happening inside and visual representation on that. So I haven't started coding anything up yet. So
okay, just keep me updated if you have some good results or you have just stuck or on something. Please always feel free to contact me. Okay.
yeah, sure.
So now I'm gonna just give you homework, and I will give you some time to work on that homework and submit it. Do you want me to give you the homework for next week or next week? So do you want 2 weeks for the homework or just 1 week? But keep in mind that after 2 weeks, you will have your midterm exam. So I personally think that giving you 1 week for this homework should be enough. What do you guys think? 1 or 2 weeks?
So if we take 1 week for this homework, the week after will be the exam.
Yeah.
And if we take 2 weeks, then the next week will be the exam.
No. If you take 2 weeks, that means after 2 weeks, you must do the exam. You must submit the homework, and you must give the mid-evaluation of the project.
Wow, that's too much. So like even if we take the homework for next week, we will have like the week after the project and the exam at the same time.
Yes, exactly.
Can we separate them because like they are two hard tasks, like the midterm and the project?
Let me see if that's possible, because I don't think we have too many lectures left.
Yeah, we don't have many lectures, but we have until December, I believe.
So 22, then 29.
Actually, like the final exam is written to be on December, for ACV.
Okay. So in that case, 29th is the final, the project mid-evaluation.
29?
No, the 5th, you mean? Oh, that's bad. Okay, so 5th will be the project evaluation completely.
Oh, okay, the final project evaluation?
Yes, will be the 5th of 11.
Okay, and okay, so there will be no mid-evaluation?
Yeah, sadly, no mid-evaluation.
Okay, can we just make a poll so like guys don't like get mad of me because I don't know what they prefer actually.
Yeah. Okay, let me just give you guys a poll. Advanced computer vision poll. Let's call this homework 2 deadline. (29th) or 23rd. Go ahead. Let me create another poll. And let me create final poll. Yeah. You can take your time, guys, to maybe look at the homework first and then decide if you want. Let me give you the homework. The homework is pretty simple, very basic stuff, nothing too fancy, right?
By the way, is homework will be like delivering a notebook only or?
Yeah, just notebook only.
Okay, thank you.
Yeah, and it just copy paste from the lab, so no worries.
And about the midterm type, so for me, I prefer written. And we can ask the others too, if they prefer written or oral, and we can decide.
The problem with written is I'm not in Innopolis, and sadly, I don't have any person who can like surveil you guys, right?
Can't we do it on Moodle?
You can do it on Moodle, but then like the last time I did it, cheating was like the name of the exam, right? So everybody had like 100%. Yeah, they just had like a Telegram group and they were just exchanging results and everybody just got 100%. And sadly, it's not fair for, you know, the students who have worked hard and the students who are trying to learn to evaluate themselves. So this is why I wanted to do something a bit more personal, something that I would evaluate every single student based on what they know, right? The questions will be exactly the same. So the same questions that you would get on the quiz will be the questions that you will get on the oral exam. The oral exam will be very simple. Majority of the grades will be between A and B. So if you asked any of the students that I had previously, I rarely have any C students or D students. All of them are between A and B, unless of course they don't show up. So yeah, things are going to be very easy. It's going to be very simple, but at least this way, I know that nobody was cheating. I know everybody just gave it their best. Everybody was answering correctly, sincerely from their heart. They were not like doing something else or getting answer from someone else.
Yeah, okay, I got you. Just last thing. So what will be the evaluation of the course?
The evaluation of the course will be based on the homeworks, based on the, what is that called? Yeah, the midterm, final exam, and the project.
And quizzes?
The quizzes, of course, are also going to be included, but I'm going to find a way to, how do we say this? Calibrate the grades. So if, for example, I see that homework 2, the grades were super bad, I would eliminate homework 2 and keep only homework 1 and homework 3, for example, or something like that. So we're going to see how the grades would be calculated once I have all the grades laid in front of me, and then I will just find a way to increase everybody's grades.
Okay, thank you.
Yeah.
And last thing, when we will receive our homework 1 grades? So like if we have like a chance to enhance or something like this.
When would you have what?
Our first homework grades.
Oh, of course. Sorry, guys. I have not graded those yet. Okay. Let me just do it now. I would do it like today or tomorrow and send you guys the grades, okay?
Okay, thank you.
Thank you so much. Thank you for reminding me. Any other questions?
Yes, please. So are we going to have a mid evaluation of the project, or just the final evaluation of the project?
That's something that we will decide based on your grades, based on your answers, right? So once everybody has answered in the deadline, tomorrow in the poll, tomorrow morning, I will tell you basically the results. If everybody says we don't do the midterm evaluation or the mid evaluation, we will not do it. If majority says we do it, we will do it.
Then one more question, please.
Yeah.
Regarding the implementation of my project with Ayo, can we use PyTorch, or can we decide to use PyTorch or TensorFlow?
Use
Either of
anything
them.
you want.
Oh, okay.
Anything.
Okay, thank you.
You're welcome.
Okay.
Any more questions? If you guys do not have any more questions, then we can close this today's lecture. Please try your best to finish the assignment like this weekend. It's a very simple assignment. It's basically literally just copy paste from the lab. So it should be pretty easy, but try to do it as soon as possible, right?
Okay.
Thank you. Let me just make sure that I gave you the correct homework. Mhm. Mhm. Yeah. Okay. So it should be this. Homework 3. Here it is. Okay, I'll just send you guys the homework right after the lecture. I'm trying to look for it, but I couldn't find it. Okay, so it's project. Right. Should be this one. Yep. Yep, this is the one. And the deadline is to be determined. Here it is. So thanks guys a lot. Thank you guys for the progress that you're making with the projects. That's very important. That's very interesting. I hope that by the end of this this course, everybody of you would have some project to put on their GitHub, and maybe some paper that they would put on their resume, something to basically help them if they want to go for a PhD or to go for some job in the research of computer vision, right? So thanks a lot. Keep up the good work, and hopefully by tomorrow morning, I will tell you guys the details, whether we will have a midterm, mid evaluation, and whether we will have the what is it called? The submission date of the second homework on next week or next week. So thanks a lot, and have a great weekend.
Sorry, just
yeah, go ahead.
Are we still going to have the midterm exam next 2 weeks?
Yes.
Okay, okay, thank you. And lastly, the file you just shared is
The what?
the Google file you just shared.
Yes.
It's requesting for access.
Ah, okay, really? Thank you. Doug?
Okay, thank you very much.
Oh, you sure?
Can I say one last thing?
Yeah, yeah, go ahead.
I'll start coding up my project like within this week, next few days. Like I am not used to like coding a big deep learning model. So if I have any problems, I hope it's okay. I can contact you on Telegram.
Yeah, feel free, certainly feel free. Yeah, no worries.
Okay, thank you very much.
You're welcome. Thank you. Can you just please confirm to me if you guys can see it? Ah, nice. It opens now. Thanks a lot. Thank you. So have a great weekend, guys. And tomorrow morning, I will tell you more information about what's coming ahead. Thanks a lot and have a great weekend.
Thank you. Bye.
Bye-bye.
Thank you. Bye-bye.
Thank you.